Hello. In this video, we will follow up on the previous one and solve the differential equation that we set up to describe this physical scenario. And we will explore the graph of that solution function and answer some questions about it. So just as a quick reminder, the scenario we're investigating is that I have a hot cup of coffee that's 95 degrees Celsius or close to boiling, and we place it in a room with an ambient temperature of 20 degrees Celsius, and we are going to assume that that ambient temperature is constant, that it's not changing. The overall goal is to explore how the temperature of the coffee changes over time, how it cools off towards room temperature as time passes. And what we did last time was we set up a differential equation that describes that rate of change of the temperature of the coffee over time, that describes how the temperature changes over time. So remember that this dc dt here is a derivative. It's a rate of change of the coffee's temperature with respect to time. And it says that that rate of change is proportional to, it's a multiple of, C minus 20, which is how much hotter the coffee is than the room temperature. So this differential equation says that the rate of change, how quickly the coffee is cooling down over time, at any moment, is a multiple, a constant multiple. It's proportional to how much hotter the coffee is than room temperature. This is a differential equation. It's an equation that involves a function and its own derivative. When I say we want a solution to this differential equation, by that I mean we're going to come up with a function, capital C of t. And remember that I'm using t as the input for time in minutes, and I'm using capital C, the output, the function, as the temperature of the coffee in degrees Celsius. That's why I picked a capital C. For now, that little constant lowercase k is something that is in the equation, and we're going to take a measurement later on and solve for what the value of that k is. It's not like the mug that I have my coffee in has printed on it, my k is negative 0.05 or something like that. We're going to have to do some measuring and some mathematics to solve for what that number is, and we'll get to that in the process of solution that we go through now. Here's what we have so far. We have this differential equation, and I'm going to start solving it by rearranging. We're going to separate the variables on separate sides. So I see a derivative where I have a dc, a derivative of c, with respect to t, with respect to time. So that's why I'm going to separate those two things onto the two sides of the equation. And in the second line, I have all of the c's on one side and all of the t's on the other. On the left side, I have the dc, and I have divided both sides by that c minus 20. I've divided it on the right so it cancels out, and that's why I end up with it in the denominator on the left side. Meanwhile, that dt that's in the bottom on the right, I can multiply through on both sides by dt, and that's why I end up with that on the right as well. Now what I have is a situation where on the left, I have a function of c in the differential dc, so I can apply the antiderivative. I can apply the integral operation on the left, and I can also apply that integration operation on the right, because if those two things were equal, then their antiderivatives, their integrals, should also be equal. Well, up to plus or minus a constant. Remember, there's that plus c that always comes in when we take an antiderivative, so that's where that's going to come from. On the right, remember that t is the variable that I'm taking an antiderivative with respect to. And so when I take an antiderivative, k is a constant, it's not the variable. So try to imagine k is like 5 or something. What's the antiderivative of 5? It's 5t. That's why I have this kt, and again, plus that unknown constant that we're going to deal with later. On the left side, to evaluate that integral, I would apply the substitution method, making w c minus 20. So its derivative dw is exactly 1 dc. So I can rewrite that integral as 1 over w dw, and that's exactly natural log of w, and that's where this antiderivative is coming from. You could also verify that by taking a derivative of the natural log of c minus 20, and you get back exactly that integrand, the function in the integral above. So this is an example of a separable differential equation. Separable in the sense that I was able to separate the c onto one side and all the t's onto the other side. And it turns out that's kind of lucky in the grand scheme of differential equations as far as they go. We were able to separate the two variables onto separate sides, so I was able to integrate both sides separately. Turns out that's really nice. Not all differential equations are separable. In fact, very few of them really are. In the context of our course, me speaking as the teacher for my class right now, we were only going to focus on Newton's law of cooling leading to this specific separable differential equation. In other calculus courses, you might explore other separable equations. You might explore non-separable differential equations. Me as the teacher speaking, are just going to explore this Newton's law of cooling just to get a flavor, a taste for what differential equations are all about. So what have we accomplished now? We have an equation that involves this function c that we'd like to continue solving for, and some constants k and lowercase c. Let's see how to deal with those now. So again, here's what we have so far. We want to solve for capital C as a function of the input variable t for time, and lowercase k is an unknown constant that came from the setup of the differential equation. So that's something we're going to have to figure out how to solve for. And lowercase c, that's also an unknown constant, but that came from the antiderivative step. So we're going to need essentially two facts about the scenario to solve for these two unknowns. We kind of have two unknowns, so we need two bits of information to solve for them. Remember that something we were given way back when at the beginning of this setup of this scenario was that the coffee's temperature at the beginning was 95 degrees Celsius. Or in other words, when t is 0, capital C is 95. So let's plug in that information into what we have so far. Let's make t 0 and c 95, and let's see what that tells us. As it turns out, that tells us what the value of little c is. But even if you didn't see that coming, have a willingness to just plug in that information and see where it goes. So it turns out I get natural log of 75 equals k times 0, or 0 plus c. And so this is just telling me straight up what the value of little c is. That initial value is telling me the value of this unknown constant. Now that I have that, I can simplify things a little bit before we start to do some more steps. I can raise e to both sides. Why would I think to do that? Well, on the left I have natural log of something, so I think e to that something would be useful because the e and the natural log, they're inverse operations, so I end up with just the inside, the c minus 20 over there. Now if I do that on one side, I have to do it on the other, so that's where the right-hand side of e to all of that stuff is coming from. And then to deal with that right-hand side, I could also exploit this property that says, an exponent base anything raised to a power times the same base raised to a different power means I'm allowed to add those exponents. And I'm really using this fact here, I guess, kind of quote-unquote in reverse, to go from here to here. To go from e to the kt plus c all in the exponent to e to the kt times, separately, e to the c. I'm using this multiplicative property, I guess, kind of backwards, you could say. But the reason I'm doing that is because what is e to the c? Well, e to the natural log of 75 is just exactly 75, and that allows me to replace that e to the c with that 75 there. So this is a little bit nicer after I even add that 20 to both sides. Now I have something that's a lot closer to getting c as a function of t. I've really isolated c on the left and all the t's are on the right, so I do have c as a function of t. I just don't yet know what that value of the constant k is going to be. And that's what we're going to address next. That constant k comes from the original differential equation, Newton's law of cooling. Depends on the physical properties of the objects. How could we find it? Well, in practice, we can just take a temperature measurement after some amount of time. So for the sake of having some numbers to work with, I have arbitrarily said, let's say I wait 5 minutes and I measure the coffee's temperature and I find that it's 85 degrees Celsius. I chose that arbitrarily. I made up these numbers. It didn't have to be 5 minutes. It could have been 1 or 10 or an hour. And it doesn't matter what measurement I get. For the coffee's temperature in Celsius, all I need is just some other data point to allow me to solve for this value of k, which is what we're going to do right now. So what we have is that function up there at the top, and what I'm gonna do is plug in the values that we just chose, that we just measured. So I'm going to plug in 5 for t, and I'm going to plug in 85 for the output for c, and let's see what that tells me. 85 comes out when I plug in 5 for t. So I have e to the k times 5, or e to the 5k. And we can start solving this by subtracting the 20 from both sides, so that's where I'm going to get the 65 that I'm about to write. And then I would want to divide both sides by 75. That's where I'm going to get the fraction that I'm about to write. And then two things here. 65 over 75, both of those numbers are divisible by 5, so I'm going to get 13 over 15. 65 is 5 13, 75 is 5 15, so that's where that's coming from. And then what I would want to do is apply a natural logarithm on both sides, because that will sort of cancel out, undo the exponentiation on the right side, and it would leave me with just the 5k up there in the exponent. And then I could finally just divide both sides by 5 to isolate for the value of k. I get 1/5 log of 13 over 15. And that's what I had typed out here already, because I saw where this is going. And if you want a number to look at to help you understand that, it's approximately negative 0.0286 or so. By the way, why is that negative? Well, 13 over 15 is smaller than 1. And I know that natural log of 1 is 0. So when I have a smaller input than 1, that's why I end up with a negative output. That's why that's happening. Okay, so now we have a solution. We have a function where I have that specific value of k. And I've chosen not to write it up there in the exponent just because it looks a little nicer to say, here is my function. I can clearly see that it's exponential something multiplied by a number and plus a number. So it gives me a better sense for the form of the function than seeing all that ugly expression for k written all up there. That would be ugly to look at. But just in case, if you want to, let me show you how to rewrite this a little bit and factor in that k and still see that it's exponential, and in fact exponential decay. So one thing I can use is that k is 1/5 a natural log of something, so I know there's a property of logarithms that says I can write that as a 1/5 power on the inside. That 1/5 I can think of as an exponent on the inside. Why would I do that? Well, that helps me when I deal with e to the kt. Another exponential fact tells me that I can write that as e to the k, all raised to the t. There I'm using the, I'm using the fact that x to the power raised to another power means I can multiply those powers. That's what I'm using kind of in reverse here again. And why is that helpful? When I write e to the k, well, I'm going to plug in this for k right here. And isn't that k a natural log of something? So when I say e to that something, it's going to be just the inside of the logarithm. I have e to the natural log of a bunch of stuff, so I'm going to see just that stuff. 13 over 15 to the 1/5. And then all of that is going to be raised to the power t. And that works out to be 13 over 15, and then that exponent property again tells me that I can write that exponent as t over 5, 1/5 of t. So this could be helpful because now I can see right here that this is exponential decay, because I have a fraction that's less than 1, and so that's why I'm going to get these solution curves that are all decaying down to the ambient room temperature. Remember that k we found was about negative 0.028. So just for comparison's sake, I have shown the actual function we're dealing with. Its graph is the green dotted line there. The others are the same function but for different values of k that are nearby. So instead of negative 0.028, I'm showing you for .01, that's that first one there, .02, that's the second one there, and so on, just to show you that they all have kind of the same shape, but the function we're dealing with is that green dotted line in the middle. Okay, let's use this function to now answer some questions about it and the situation we're dealing with. What would be the temperature of the coffee after half an hour? Well, remember that T is measured in minutes. Always pay close attention to the units of measurement. So when I say half an hour, that means T equals 30 minutes. So to evaluate this, I'm going to say, what is C of 30? What happens when I plug in 30 for T? Get 20 plus 75 e to the k times T, which is 30. So I'm going to spare you the trouble of crunching these numbers and just tell you that this works out to be about 51.78, and the units on that are degrees Celsius. That's this data point over here, where I have 30 as the input, and the output is, you can see, just a little bit above 50, that 51.78. What's the temperature after 1 hour? Well, 1 hour is 60 minutes, so I'm going to plug in T equals 60, and I'm going to do pretty much the same thing. Crunch those numbers, have a 60 instead of a 30 up there, and I'll again spare you the trouble and say that works out to be about 33.47 degrees Celsius, and that's that second data point I've marked in blue on the graph there. When T is 60, the output is there a little bit above 30, that's that 33.47 number. What's the average temperature over the first hour? Well, to answer this, we'd have to think back to an earlier video where I showed you the average of a function formula. And over the first hour, so remember that means from T equals 0 to 60. The average value of a function is obtained by integrating the function between those time values across that domain, and then dividing by the width of that domain, the size. So this is saying integrate, find the area under the curve over the first 60 minutes, and then divide by 60. And so overall, this represents the average height of the curve between these two endpoints, from 0 to T equals 60. We're going to get the average height. So take a second to just look and guess where you think that might be. It's very steep at first, so it's very tall, and then it's much lower and flattening out. So I'm going to guess that the average height's going to be somewhere around here, quite a bit above 50, and I think it's actually going to be even above that value we found at half an hour. Let's see how this goes. Well, let's see, I'm going to have 1 over 60, and then we can do an antiderivative of C as we go here. What's the antiderivative of 20? It's just 20t. What's the antiderivative of that exponential piece? Well, it comes out to be 75 over k e to the kt. Doing a quick little substitution there, you can check by taking a derivative. If I took the derivative of e to the kt, it would be itself e to the kt times k. That pops out from the chain rule. And that's why I have that division by k. Remember that the substitution rule is really the chain rule in reverse. So I'm just going to plug in those values for 60 and 0. So I'm going to have 20 times 60. And when I plug in 0, be careful, because one of those terms, 20 times 0, that cancels out. But e to the 0 is not 0, it's 1. So just be careful about evaluating this and crunching all these numbers. And as usual, I'll save you a little bit of trouble and tell you that this works out to be about 55.83. And that's somewhere around here on the graph. So like I said, a little bit above the actual temperature of the coffee after half an hour. The average over the first hour is a little bit higher than that, and that's because of how steep the decay was back at the beginning. This curve is so much higher over here than it is down here when it's starting to flatten out. So that average over the first hour is a little bit above the actual temperature after half an hour. Here's another question. What happens as time goes on? What is the limit of this function as t, the input time, goes to infinity? Well, from the graph, I can see that this looks like a horizontal asymptote. I'm going to predict that this is going to equal 20. But remember, that was also the constant ambient room temperature. And that should match up with your physical intuition. If you take a hot cup of liquid and you put it in a room and you wait a while, eventually it becomes room temperature. It is almost the same temperature exactly as the room. So it makes sense that we're seeing that on the graph. How can I also see that from the function itself? Let's take a limit as t goes to infinity of e to the kt. In this case, it's going to be 0 because k is negative, so we're seeing exponential decay from that term. And you could even see that from this other form of the function that I've written here. Because 13 over 15 is less than 1, multiplying a number less than 1 by itself a whole bunch of times in a row makes the result smaller and smaller and smaller. It's going to decrease to 0. And so that's why I'm going to see that limit of the whole function, capital C, approach just the 20. When I say this limit here is 0, that means when I take a limit of the whole thing, this term is going to disappear away to 0, because it's 75 times 0, and I would just be left with the 20 itself. All right, one final question. Let's say I am very particular about my coffee, and I only will drink it when it has cooled off to exactly 158 degrees Fahrenheit. No, I'm not actually so particular. I will drink coffee at just about any temperature as long as it doesn't burn my mouth. But I did some Googling around, and I found that this is, for some people, an optimal temperature, let's say. So how many minutes would I have to wait after putting the coffee in the room? If I set a stopwatch, when can I pick up the coffee and drink and have the most ecstatic experience I could have with this coffee? Well, there's a couple things to do here. There's a reason I chose to write this as degrees Fahrenheit, to remind you that I should be able to convert this to Celsius. So, by the way, that's C equals 70 degrees. You can look up on Google for yourself how to convert from Fahrenheit to Celsius. Now that means I'm going to set C of t equal to 70 and try to solve for t to figure out the time when this would happen. So let's see, I'm going to subtract 20 from both sides, so that's where I'm going to get this 50 from. I'm going to divide both sides by 75, so 50 over 75, that's 2/3, that's where that's coming from. And by the way, I'm continuing to write k, even though I know what number it is, because I don't want to have to write this 1/5 log of a fraction over and over and over. I'll plug that in at the very end when I skip over to my calculator to crunch some numbers. I'll just keep writing k, because it's a lot shorter for me. Let's apply a natural log on both sides. So I have log of 2/3 equals, now natural log of e to the something returns that something. So finally I have t equals log of 2/3 divided by k. Now I can use that actual value for k that we had way back there and plug it in, crunch some numbers. I'll save you some time. Turns out to be about 14.17, and remember that's in minutes. So this is saying after about 14 minutes or so, that's when my coffee's temperature will have decreased from 95 degrees down to this optimal 70 degrees Celsius that I've chosen.